Hi all, and thank you for your interest in this work. My name is Gaoping Huang. Today I will be talking about Vipo, Spatial-Visual Programming with Functions for Robot-IoT Workflows. As we are aware, mobile robots and IoT machines are being increasingly deployed in factories. As a result, human operators, robots, and IoT machines are tightly integrated in the manufacturing environment. This is part of a recent trend toward Internet of Robotic Things. At the same time, modern factories are embracing Industry 4.0, in which the production becomes more flexible, modular, and customizable. In other words, the workflows often need to be changed or reused, which requires workers to be able to program workflows by themselves. This brings us to the core question of our research. Can we enable workers to efficiently program workflows within a dynamic environment of robots and IoT machines? This breaks down into two goals. First is to enable programming workflows in a readable and efficient way. Here are some existing work of task planning. Blockly, for example, is a visual programming that uses a set of blocks to program commands and logics. Also, Node-RED, it uses a different style, a node-link style to give commands and logics. On the other hand, some work has explored the idea of drawing the commands in the spatial domain. For example, Visor, they draw the command on top of the airport map. Similarly, FetchCore, a commercial product, they draw the commands on top of the factory map. A brief summary. Some visual programming languages are generic purpose. They have functions so they can support flexible and complex workflows, while others, they are drawn in the spatial domain. They do not have functions so they can support relatively simple workflows. Therefore, we present Vipo to support both. But first of all, why do people care about spatial and functions? And first, why spatial? The reason is that activities of robots are spatial-oriented. Consider this simple workflow in which the robot is asked to move to location A to pick one object, then move to location B and drop there. Consider a diagram below. Here we can see the source and destination clearly, the direction and relative distance, so which is more straightforward. Next, why functions? Consider this workflow. Again, we have two similar workflows. The only difference is that the numbers to pick is different. Without functions, users have to duplicate those workflows, which is very tedious. With functions, however, they can encapsulate those details and make it more compact and scalable. Therefore, we developed Vipo IDE to support spatial and functions. In the middle, we have the layout map of the factory, and also we put the icons of the IoT machines on top of the factory layout map. On the left-hand side, we have a set of tools to allow users to program robots and IoT machines. On the right-hand side, users can create one or more functions. Specifically, workers can use spatial visual constructs to specify steps for robots, such as move, pick, drop, and carry. Also, workers can use in situ constructs to specify steps for IoT machines, such as charging or pen mixing. They can also give some values to make it more customizable, if necessary. Here is a sample program that combines the robots and IoT machines. It first asks the robot to carry one pen cam from the pen inventory to the pen mixer. Then the pen mixer will work for 5 minutes. Then the robot will carry it away to another place. Instead of sequential and linear workflows, some workflows may depend on the status of IoT machines to conditionally choose the path. For example, we can use the job status of the pen mixer to decide which pen mixer to use. If the job status is greater than 80%, we choose the left one, otherwise we choose the right one. Then functions. Before I mention how we design the function in the spatial and visual domain, let's look at the properties of a function in a textual domain. Textual programming language. As you can see, the function has a name, 0 or more parameters, and a function body. To reuse this function, we can make function calls with the same or different values. Based on those properties, we design our function in a similar way. First, we enable users to create variables, and then we can further use them in the variables, in the workflows. Next is to enable function call. Here is a naive way of function call. Given this sample workflow, we simplify it into fx with 4 nodes. We have another workflow which has 6 nodes. The gx shares the same 4 nodes as fx. Therefore, to avoid duplication, we want to make gx to call fx. And here gx is the caller, while fx is a callee that is being called. To visualize this caller-callee relationship, we simply wrap the callee by the caller. And this becomes a path layouting problem. Therefore, we find some related work in some other spatial domain, such as the geomaps. Here is an example where people have explored the option to make the routes with occultation or not. However, those approaches have some limitations, especially when there are multiple functions calling the same callee. For example, let's consider this example with 2 callers, the green and the red one. They are calling the same callee, blue one. The callers are wrapping the callee. As you can imagine, if the number of callers is increasing, the whole path will become wider and wider, which is not scalable in the spatial domain. We consider to use 3D to make it more compact. However, this suffers the same problem. We cannot support a lot of colors in 3D version. We took an opposite approach by wrapping the color by the callee, also a corresponding 3D representation. However, those approaches suffer from the same scalability problems. Even worse, they cannot support nested function calls. The main reason is that we are trying to visualize the caller and callee at the same time. The conclusion or our solution is that we need to hide the implementation details of those callee function. Once we hide the callee, we can simply use their function name and the color to represent the function call. And users may have the need to preview the detail of the callee. Therefore, we provide a functionality so that user can click on the expand button, and then they can temporarily see the internal detail of this callee. Once they can make function calls, then the next step is to enable them to pass different values to the callee so that they can achieve customization and reuse. Especially, some callee function may involve multiple machines. They may want to pass a different machine in the workflow. Here, we provide a unique way. First, they can click on the expand button, then they can see the internal detail. They can click on the blue switch button of the old machine, and then they can click on the new machine. All the constructs on the old machine will be automatically transferred to the new machine. In this way, the workflow will use a different location. So far, we've seen how to program the robot and IoT machines using the Vipo language. This brings us to the next goal of making the robot and machines to behave like a unified system, so that in the IDE, they can be programmed in a very similar way. We implemented a 3-layer architecture. At the bottom, the IoT and robots are the execution layer. They keep broadcasting their status and functionalities to the ROS master in terms of RDF message. RDF stands for Resource Description Framework. ROS stands for Robot Operating System. So the ROS master forwards the RDF message to the Vipo editor, and the Vipo IDE will populate the UI automatically using those messages. I will explain this process in the next slide. After the user programming those workflows, the visual program will be compiled into textual script and sent to ROS master. Then the ROS master will further compile it into ROS script to control the execution of IoT and robots. Here is the sample RDF message. After receiving the sample RDF message in the IDE, the system can automatically use the name to populate the drop-down list and also use the methods to populate the supported APIs. We evaluated our system with two user studies. First, we want to understand if spatial-oriented visual programming can enhance efficiency and comprehension. We compared Vipo language to a non-spatial language called Blockly. We recruited 12 participants and randomly partitioned them into two groups. In the first group, each participant was asked to complete 6 tasks with Vipo, then the same tasks with Blockly. In the second group, the task order is reversed. We recorded the screen while they were doing the task. Afterwards, we calculated the total completion time and the total errors. In terms of efficiency and the total completion time, the time of Blockly is significantly longer than that of Vipo, which implies that with spatial constructs, programming took less time. In terms of comprehension, as I mentioned earlier, participants were asked to complete 6 tasks. In the last task, participants were asked to read programs in 2 languages that are created by the researchers. And then they need to answer questions such as identifying the source and destination and the optimal steps. The total score is 5. As you can see, Vipo received higher scores than Blockly. This suggests that with spatial constructs, programs were more comprehensible. Next, we want to understand if functions can enhance efficiency and correctness. We compare Vipo with functions versus Vipo without functions. We recruited 10 participants, and they were given 3 tasks for warm-up. After that, we randomly split them into 2 groups. In the first group, each participant was asked to complete 3 tasks with functions, then without functions. In the other group, the task order was reversed. Again, we compared the total completion time. In this case, the total completion time had no significant difference. However, if we took a closer look at the subtasks of each task, we can see a trend of time decrease and time change. For example, one task has 3 subtasks. In the first subtask, participants were asked to program the workflow from scratch. Then for the second and the third subtask, if they can use functions, they can make function calls. Otherwise, they have to create the function again. As you can see, the time spent in each task decreased if they are using function calls and remain relatively constant if they are not using functions. Secondly, we measure the total errors. As you can see, Vipo with functions received lower score than Vipo without functions. This implies that using functions was more error-prone. This is surprising but understandable. To use function calls, participants need to learn more concepts such as defining parameters, making function calls, and passing different values, which is more error-prone. The main takeaway of this presentation is that Vipo unifies the programming for robot-IoT workflows through a spatial visual language with functions and a communication architecture. Thank you for watching.